are making progress. So we will revise RNN one more time, just quickly today, and after that we will have presentation today from Gurav. So I mean RNN, we talked about it last time, and we talked about the limitations of feed-forward neural network, and we said that it cannot handle fixed input size. It can only handle fixed input size. So this is a problem in RNN. So it cannot deal with sequences of data. So we can deal with sequence of data, but maybe we need to have some tricks. We can use zero padding to address handling of smaller inputs. So sometimes when you design your model, you design it for some fixed input, but to deal with smaller inputs, in this case, we can use zero padding, maybe from left side or from right side, right? So in RNN, sometimes we can use it from the right-hand side. So the model breaks down when input exceeds the fixed input size. I mean, this is a problem, of course. And the model size will grow dynamically with the size of the input sequence. So the input sequence will increase. We need to redesign the whole system, and the whole size of the system will dramatically increase. And in case of feed-forward neural network, it does not require any data preparation. So we can just use the data as it is. But in case of RNN, we need to do some data preparation. From the point, we need to reshape the input data to be in the form of a 3D matrix. But this is not the case in case of feed-forward neural network. And of course, also feed-forward neural network, it cannot capture long-range dependencies between input vectors. So this is a problem because we don't have a memory in feed-forward neural network. So there is no connections between different sequences. So if you can say it like this. So in case of sequence to sequence or sequence to one or whatever, so it's we can use this left to right reading of the input sequence. We have a sequence, so we need to read it from left to right as you are reading English. Maybe if you have different language, you can change this one. So for example, if you are dealing with other language, it could be top to bottom, it could be maybe right to left. So it's according to the problem. But this is in the general case, it's left to right reading of the input sequence. Update the state vector incrementally. We need here to update the state vector because the state vector here will get some, this is a memory in fact. So if you need to represent some syntactic or semantic context from the beginning until the current input or until the end, we need to have this. We need to have this state, and we need to update the state each time. And as you know, in RNN, the state is function of current input and last state. We need to integrate the current input word into the state. The state can serve as a memory which allows patterns to be remembered over long-range context. So in case if we are working with sequence to sequence, for example, or sequential data sets, in case of sequential, we can just say in general, it's a sequential data set. We need to have a state. We don't have a state here, in fact, in feed-forward. So we need to use RNN. Recurrent neural network, it's something old, in fact. So as we mentioned last time, it was introduced in 1980, but it have gained popularity, in fact, only recently due to the hardware development that we have today to train it. So RNN is different from feed-forward because of recurrent layers. We have some recurrent layers that enable it to propagate information between rows of the same layer and maintain state between uses of the network. So each time, when we have some input sequence, we will scan this input sequence from left to right, for example, and each time we will update the state, and we will share the model parameters between different updates. So in this case, we can keep some information, or we can maintain a kind of a state or a memory between different uses of the memory. As you can see, feed-forward neural network, we have some input layers, some hidden layers, and some output layers. But in case of RNN, for example, we have input, we have some recurrent layers, we have an initial state, and we have here some initial state. We can say it's H0. We need to calculate the new state, for example, H1 or HT+1. So this state will be a function of the previous state and the current input. And of course, the output will be a function of the state. There is one model. It's a very simple model called Vanilla RNN, and this model uses a standard perceptor layer with nonlinear activation to achieve recurrent state input combination. There are several, variants of RNN with a stronger representation power. In vanilla RNN, we calculate the output sequences. We don't calculate the output, we calculate the states, in fact. So we calculate the states as a function of the current input and the previous state. And this is a very simple one. So we calculate output sequences, H1, H2, Hn, given input sequence X1 to Xn, recurrently from the initial state H0. So we calculate, the state according to the previous state and the current input xt. So according to this equation. So each time when we train this one step by step, each time we calculate the state as a function of the current input and the previous state. And it will be simple like this one. It's non-linear function, non-linear activation function, and the input will be omega h times h. So this one you can say that it's a state to state, right? Or hidden to hidden. This one input to this one, it's inputs omega x times xt plus bias ph. F is nonlinear activation function such as hyperbolic tangent. WH, WX, and pH are model parameters which we share among different time steps, because in each time step we train the model and we propagate the states from one time step to the next time step, and also we share the model parameters between different time steps. So RNN looks very different from MLP and CNN due to the recurrent time steps. We have here this recurrent time steps which we don't have in MLP. In MLP, the output from lower layer is fed to an input to an upper. It's like this one, if we can put it in the same structure. So the input from the bottom layer will be propagated to the upper layers in that direction. But in case of RNN, the output of a network layer is wired back as an input to itself. So we have this kind of feedback or recurrent. We have this kind of recurrent layer or kind of feedback which does not exist in MLP or CNN. So this one here, you can say that it's, the structure is based on layers. Maybe here the structure is based on time steps. If you want to unfold it, we have this as a model. So in fact, this is our model. But when you are training it, in fact, we train it over a number of time steps. So you can unfold it over the time steps like this one. And each time we will share the state. Each time we will calculate, we will update the state. This state will propagate between different time steps. So you can just say that here t equal, this one maybe it's t time step t, this one it's t minus 1, this one is t plus 1, for example. So if you don't wipe away the previous state ht minus 1 when calculating ht, but instead record all the history data, we can effectively unfold the recurrent state transition process into a linear chain. So the unfolded version of RNN is standard MLP with lower layer towards the left and the upper layer towards the right. You can just say that this one now looks like a feed-forward neural network where we provide, where this one, it's the bottom layer, for example, and this one, it's the upper layer. So you can say that we unfold it in terms of time steps, not in terms of layers as it is in MLP and CNN. The mathematics, the steps can be written as one function. Each time in this unfolded case, we calculate if we will record all states. So we will have H1, H2, and Hn, for example, if we have n time steps. So this is our RNN model. So the initial state H0 can be set to 0 or can be defined as randomly initialized parameters, this initial states. Because when you are starting your problem, for example, maybe you are waiting some data coming from a sensor. So at the beginning, we don't have any information, in fact. So we can initialize H0 to 0, or we can initialize H0 to some small random parameter random number. The final vector Hn can be used for representing the whole sequence, in fact. So the final state here will be representing the whole sequence of input. RNN are trained using unfolded representation using backpropagation through time. This algorithm, they call it backpropagation through time, or BPTT. the training is identical to MLP, except the number of layers is dynamic to the input and it can be large. I mean, here you need to decide number of time steps, right? So it's dynamic. I mean, we have the same. I mean, the model is, you can say that the model is static, the model parameter is fixed, but we train the model each time step. Number of time steps, this is a hyperparameter which you need to decide. RNN are subjected to gradient exploding and vanishing problems. So we have this exploding gradient and vanishing gradient problems. And to solve this problem, they developed different model, which is LSTM, which has better capability to deal with exploding gradient and vanishing gradient problems. So it's just the only difference between this and standard MLP is the size of the network dynamically grows with the size of the input sequence. Yes, in case of MLP, if the size of the input sequence will increase, the whole size of your model will increase, number of parameters will increase, right? But in case of RNN, well, no, we don't have this one because we can, you can just say we have a sequence of input and we will scan this one in a certain number of time steps. And in each time step, we will retrain the model. So the model will be the same even if the size of the input sequence will be will be different. So if it is small, if it is bigger, we don't care because the idea here is to divide this input sequence into sections, for example, and each time we train the model in each time step, and we share model parameters between each time steps. So the trick for RNN to achieve dynamic size is sharing model parameters across layers. So we just share those model parameters. So each time we have some input sequence, we will train the model on one part, for example, one section. And after that, we will go to the next section. Maybe you can have some overlap. Maybe you don't have an overlap. This is something you need to decide. And the idea here is to share the model parameters between each time step. And in this case, we can keep the model size static or I mean fixed, regardless of the size of the input sequence. Here, input X is the input, H is the state, Y is the output. A, B, C, this is the model parameters, weights and bias, which is shared over each time step. So the current input at any given time, T, is the combination of the input XT and HT minus 1, which is correct. If it is vanilla RNN, I mean, it's not the output in fact, but it's the state, right? So the state will be function of the current input XT and the previous state HT minus 1. Yes, so recurrent connection allows the network to remember what it learned in the previous step. The unrolled RNN graph can be imagined as how the recurrent connection flows from one step to another, allowing the RNN cell to show this memory-like characteristics. This memory-like characteristics, it's we memorize previous input summarized in the state. So at some step, the state will represent the whole context, the whole input sequences. RNN can memorize previous inputs due to the initial memory in the previous states. Trainings RNN usually executed one step at a time. Yeah. I mean, the equations for this RNN, as I told you, we have, it's very simple. So we have the hidden state, we need to update the states. We need to calculate each time. In fact, each time step, we need to update the states and we need to calculate the output, right? So how can we update the states? HT, the current state will be function of the current input, which is XT, and the previous state. So it will be like this one. And the phi, it's nonlinear activation function. It could be hyperbolic tangent or whatever. So we have omega x times x plus omega h times h plus ph. This is the bias. And once you calculate or update the states, in this case, in fact, you can calculate the output or update the output. So the output also will be a nonlinear activation function of the state, current state. So it will be omega y times h plus py. This function will be softmax, for example, if you are calculating the probability of the next character, for example. So this is also some hyperparameter which you need to decide. So model parameters here, it's input to hidden, and hidden to hidden, hidden to output, hidden bias, and output bias. I mean, this is a hidden bias, this is output bias. This omega x, in fact, it's input to hidden, right? This is input to hidden. WH here, it's hidden to hidden. And the WY, it's hidden to output, right? So this is the math of RNN. So just again, comparison to feed-forward neural network. Feed-forward neural network allows information to flow only in the forward direction from the input nodes through the hidden layers and to the output nodes. So there is no cycles or loops in the network in case of FNN or MLP. In case of MLP, also the decisions are based on the current input. So we have some input here, and we have decision. I mean, this layer here, it will be maybe this is maybe this layer will be softmax layer. It will make some decisions. So the decisions which are done here will be based on the current input in the input layer. So it does not memorize any past data, and there is no future scope. I mean, in feed-forward neural network are used in general regression and classification problems. It cannot handle sequential data. It considers only the current input. It cannot memorize previous inputs. So if you want to make some comparisons between feed-forward neural network and RNN, for example. Different applications of RNN, it's image captioning, for example, it's one-to-many. So the input will be maybe an image, and the output will be a sequence. So we call it one-to-many. Time series prediction, which is one-to-one, or maybe one-to-many, for example. Because we have a time series, it could be one-to-one, for example. So we use the last value for predicting the current value or future value, right? It could be many-to-one, for example, which means we use recent values, maybe recent 5 readings for predicting the current value or future value. We can use it for natural language processing, and in this case, it could be, for example, many-to-one, or it could be many-to-many. Many-to-one when it's sentiment analysis, for example. I have a text like this data, this video, this movies reviews database. So it's many-to-one. So we have some reviews from people, and we need to decide if this one is positive or negative. So the input will be a sequence, and the output will be just maybe +1 and the -1. So we call it sentiment analysis. In case of machine translation, we translate input into different language. So it will be sequence to sequence. So maybe the input will be English and the output will be Danish, for example, or Norwegian, for example. So in this case, it's many-to-many.
Can I ask a question?
Yes, please.
How many? Can you go to the last slide, the last one?
This one?
The one with the timestamps on the RNN. Yeah, yes. That's right. Yeah, that's. In here, in hidden states, we say that it's HT-1, right? It's like, can we have HT-2, T-N? It's like how many timestamps can we go back?
No, but in fact, each HT, it will represent all previous context, right? So you don't need to use HT- because it will be just, it aggregates. In fact, you can just each time, we aggregate the previous state into the new state. So maybe this is the most recent update. So this is the most maybe useful one, because you control how much information you will get from this one using omega h, right? So you control it by this one. So how much information we need to keep from the previous states, we can control it using WH, for example. But we use the previous state to update the current state. If the previous state has some information, some memory, we try to integrate this one right into the current hidden state. So you don't need to go to HT-2, HT-3. We don't need this one because we have this kind of recurrent. We have this recurrent with a kind of feedback.
It's like a Markov chain of the order of 1. I said that can we use Markov chain of the highest order? It's like order 2 or order 3. It's like at the current state, we use the coefficients of the HT-N, for example, like to n, go back to n, and also like the information of HT-1 as well. It's like all together one coefficient. I don't know if I can say
yes.
what in my mind.
But I mean, according to the structure of RNN, we have this kind of recurrent here, right?
Yes.
So each time we update the states, and it means that we try to control how much information we will keep from previous states, and we agree that each state will be function of the previous state as the current input. So you have the current input. What about all recent inputs? So all those recent inputs will be embedded in the hidden state. So all the informations or those historical information will be embedded in the previous states. So now I have the current input xt. I have here xt, and I have here the previous state, which is ht minus 1. And I will use this one for calculating or updating ht. So to calculate ht. So just imagine that ht minus 1, each time, this is the memory, in fact. This is the context which we will learn, we will keep in mind from the previous inputs. Because, so now you have xt. What about xt minus 1? What about xt minus 2? All those informations will be embedded in this ht minus 1, right? So each time step, right, you update the state using all those historical information. Now I'm using xt, so you can just say, that, okay, what about the previous information? What is the historical information? Where is my memory here? The memory here will be implemented in the state. So ht minus 1 will represent all informations from xt minus 1, xt minus 2, xt minus 3, and so on, right?
Okay, thank you.
Yeah. So this is 1 to 1, for example, and this one in 1 we can use it in time series, for example, for predicting. So we can just use a single input for predicting some values. So we have some single input. So maybe it's a time series, for example, where we have only one time series or we have only one feature. So we can just use last value for predicting value for tomorrow, for example. So it could be 1 to 1, or it could be also many to 1. So we can just have a window of values, and we can use those all historical values for predicting value of tomorrow. Image captioning, we have a picture, for example, and we need to try to find a description of this picture, right? We need to find a caption. I have this one, and I need to get a description. So this is picture, and I want to find a description of it. So for example, we need to train a model which can translate this picture into a dog catching a ball in mid-air, for example. So how can we do this? The input here will be 1, right, which is an image, and the output in this case will be a sequence. So it's 1 to many, for example. You can just call it 1 to many. So the input here will be an image, RGB image, for example, and the output will be a sequence of words, for example. In sentiment analysis, we have multiple inputs, which is a sentence. It could be a sentence, or it could be a review, movie review, for example, like movies reviews database, for example. So in this case, we have the input will be a text, and the output will be just 1. This one, it could be +1 and -1. So we call it sentiment analysis. So you have some reviews, and you want to classify it, which one has positive review, which has negative review. So in this case, we can use it for sentiment analysis, and this one has very important applications. For example, Twitters, for example, when you try to analyze some information from Twitter, for example, about economy, for example, positive view or negative view, what is the feeling of people, stock market, and stuff like this. So you need to check this one. So you can train a model to try to convert each input review into one, which is classify it into +1 or -1, for example. Yes. So for example, the sentence here, if you read the first one, when it rains, maybe when it rains, so this is something negative, maybe look for rainbows. So in one it's positive. When it's dark, so now it's a negative, look for stars, so it will become positive. So in this case, is it positive, is it negative? So if you will take it part by part, maybe you will not be able to classify it, but we need to keep a memory to try to memorize the whole context of the whole review and to try to find the correct sentiment for it. So in this case, RNN takes sequence of inputs and generates single output. In sentiment analysis, we have a sentence which need to be classified into a single output, and this output will be positive or negative sentiments. In machine translation, we have input sequence and we will have output sequence, so we call it many to many. So the input sequence, it could be a sentence in English, for example, and we need to translate it to Chinese, for example. So in this case, it will be sequence to sequence, right? But we need to be careful about the direction. Should we scan it from left to right? Should we scan in Arabic, for example, we scan text from right to left. In Japanese, for example, is a top to bottom, bottom, something like this one. So we need to be careful about the direction in each language, and also inside the network in itself, the mechanism. For example, if we are using CNN, for example, how we will use, I mean, the filters, how the filters will move. Is it from left to right, or from left to right, or from right to left? Because if you will not follow, I mean, the structure of the language, maybe you will destroy the context of the language. So in this case, RNN takes a sequence of inputs from source language and generate a sequence of outputs of target language. Yes. This vanishing gradient problem, RNN enables you to model time-dependent and sequential data problems, such as stock market predictions, machine translations, and text generation. So we have a problem in RNN. This is a problem of vanishing gradient, and therefore it is hard to train. And therefore, I mean, usually you don't use RNN for long sequence of data. If you want to memorize, I mean, long dependencies, we cannot use RNN in fact, and it's better to use maybe LSTM. So the gradient carry information used in RNN, and when the gradient becomes too small, the parameter updates becomes insignificant. So we will not be able to train the model, and this makes the learning of long data sequences difficult. So RNN layers uses for loop to iterate over time steps. So you can just imagine that it's a model, and this model uses a for loop to iterate over time the time steps of the sequence, while maintaining an internal state that includes information about the time steps it has seen so far. So each time we train it in a for loop, and each time we maintain the states, and we share the model parameters between each time steps. And therefore, the size will not impacted by the size of the input sequence, because we can just change the time steps. LSTM versus RNN. LSTM, which stands for long short-term memory, deal with these problems by introducing new gates such as input and forget gates, which allow for a better control over the gradient flow and enable better preservation of long-range dependencies. The long-range dependency in RNN is resolved by increasing the number of repeating layers in LSTM. So LSTM, it's more complex model, and it's slower in fact. So RNN it's faster when you train it, but it has an advantage that it can keep those long-term dependencies much better compared to RNN.
I'm sorry.
Yeah.
Can you explain a little bit more about why RNNs have vanishing gradients? I don't.
Yeah, I guess. Yeah. I guess we will have. Maybe I will have some slides here.
Okay.
Yeah. But it's because I didn't go into mathematics, in fact, but because we have those long independencies. I have a sequence, and I need to keep the gradient. So, for example, I mean, in this structure here, for example, we have initial states. We initialize this one by random value or by zero value, and we train the model one time in one time step. This is one time step. For example, I can say it's t equal 1, for example. Now we will go to the next time step, which is t equal 2. So we need to keep some gradient. We need to have some flow of gradient between different time steps. So we have a problem here, in fact, when we in the gradient flow between t equal 1 to t equal 2, it will be much smaller here. And after that, we will go to the next time steps, which is t equals 3. It will be much smaller here. So maybe the performance will be okay here, but in the next time steps, maybe it will be much less. In t equals 3, it will be much less. And you repeat this process several times. So the flow of gradient, it will be much smaller. It will get smaller and smaller according to the sequence. What is the size of the sequence, or how many time steps? So so this one will perform very well RNN if you have short sequences, or if you have short time steps or small time steps, because it can keep memorizing things, and it has a memory, in fact, but it's not long-term memory. It can memorize short. It can say it's short-term memory, so I can memorize recent things, but not very old stuff. So you can just imagine it like this one, because of this vanishing gradient problem. So because of the flow of the gradient from between each time steps, it will get smaller and smaller, and this one will impact the training. So at some point here, the gradient will be very, very small, and at t, for example, equals 3 or at t equal n, it will not possible to train the model. So you will not be able to keep updating your state and your outputs, for example. So in this case, I mean, you will keep training, but it does not memorize anything, right? So I can remember something from t equal 1, t equal 2, but here when it's t equals 3 to equal 4, I cannot update my states because the gradient becomes very, very small. So I will not be able to adjust or update update the states. You know that from the equation, ht is function of, right? It's function of it's omega x plus omega h multiplied by h, right? This one t minus 1. This one it will be ht, right? Plus bias of h, for example. So the problem here, we need to adjust omega. We need to adjust omega x and omega h here, omega x and omega h, and to update those weights, we need to have gradient. So when the gradient becomes very small, we will not be able to adjust. I mean, those values will stay as it is, because partial delta omega, it will be something using backpropagation. So it will be, this delta omega will be very small, delta omega h and delta omega x. It will be very small. So we'll not be able to adjust omega x and omega x. So at some point, you will not be able to adjust, to update your states, and you will just keep the old states, right? Because if I couldn't update ht, I will calculate here h1, for example. So I calculated h1 here, and I will use this equation for calculating h2 in the next time step, for example. So here maybe we will have some adjustments, some updates. So I will keep the context from this steps to this one here. So when you go to h3, for example, I mean, this delta omega will be much smaller. So you will not be able to adjust. You will not be able to update h3, in fact, and maybe h3 will be the same as h2, right? So it's a problem. We cannot learn the context. We cannot train the model because of the gradient problem. But in case of LSTM, it has different structure and better control for the flow of gradient between different time steps. There are lots of structures. In fact, for example, deep RNN, for example, you can have different layers of RNN layers. You can build a neural network which has different, a deep RNN where we have different layers of RNN or LSTM in your model. You can call it deep RNN, for example. Bidirectional, I mean, we need to read those stuff. Local and global information, for example. So when you train your model, you will get some local outputs. I mean, each time step, you will have some local outputs. Each time step, you will get some different local outputs. In each time step, you will get some local output. But maybe the last one will be local and global. So maybe sometimes you can use the global outputs in each time step for the next layer. So you can propagate those values to the next layer, those local outputs, or you can just use only the global output, right? You can just, it's a global information. And of course, we should know that maybe the global output, it combines all those local informations inside it, for example. So the structure, using a global feature for classification, you can build your model. This is RNN model, one layer, for example, and the output, the global feature from this one, you will feed it to a fully connected layer. Maybe this one will be used for classification, for example. You can use, for example, in sentiment analysis, we can use RNN, and this RNN will deal with a sequence of inputs, and you will get this global feature or local features. You can feed those global features or local features to the next layer, which is fully connected layer. Maybe this layer would be softmax layer for maybe predicting next word or whatever. So maybe we can use global features. Maybe also we can use local features. So this is, it depends what kind of information you will feed to the next layer. RNN APIs in Keras, we have LSTM layer. So if you want to use LSTM, you just need to import it from keras.layers.lstm. We have also something called the gated recurrent unit, or GRU layer. You can get it from keras.layers.gru. GRU, in fact, it's a small version, or it's a version of LSTM. So GRU, this gated recurrent unit, it's a simple version of LSTM, because LSTM, it's complex and it takes time for training because it's a complex model. But this gated recurrent unit, it's simple version of LSTM. But this is how if you want to import it from Keras, you need to import it GRU API from keras.layers.gru. So it's a similar, in fact, to LSTM without output gate. So it's just a simple version of LSTM. Why? Because LSTM, it takes more time. I mean, LSTM, it's more complex model, and it's slower, and it takes time for training. So if you want to use a simple version, so GRU is a simple version of LSTM, and it is the same, but it has only 2 gates. In LSTM, we have 3 gates, and GRU, we have only 2 gates. So it's a simple version of LSTM. We have also simple RNN. I guess this is a vanilla RNN. And you can import it from keras.layers.sample.rnn. So it's the difference between RNN and the simple RNN that the output from the previous time steps is fed to the next time steps directly. We don't use here hidden to output, right? We don't use hidden to output. We can just calculate the output directly from the states. Yes. So the difference between simple RNN and RNN. In RNN, this is the standard model, right? So the output here, it's a soft max of you can hidden to output, right? So the output here is a soft max of hidden to output, but here the output will be soft max of the states directly. You just calculate soft max of the states to calculate the output. So simple RNN, it's a simple version of RNN. So so the difference, it's not in the hidden state, not updating the hidden states, but it's calculating the output. So we have this standard equation for updating the states. This is a standard. This is common between the 2 models. But in case of RNN, we use the softmax function, and it's this one. It's hidden to output. This one, it's hidden to output, right? But in case of simple RNN, we calculate YT directly from HT by applying softmax function. So this is the difference between RNN and simple RNN. So simple RNN, it's a simple version of RNN. Time prediction, time series prediction using RNN. I mean, we are working with sequential data or time series data. And maybe this one, it's maybe not. This is time series, which is simply a series of data points ordered in time. Data points are measured at successive equally spaced points in time. In a time series, time is often the independent variable, and the goal is usually to make forecast for the future. I mean, in this any time series, we have some characteristics: autocorrelation, for example, seasonality, stationarity, for example. So this is features of any time series. We had this example last time, this airline passenger dataset. We have this dataset from 1949, from January 1949. This is number of passengers in 1,000. So this is the number of passengers, and it's in 144 months from January 1949 to December 1960. So it's 12 years data with 144 observations. So when we plot it, it will be like this one. So we have here time or months, for example. This is number of passengers in 1,000. And this is my time data set. And the goal here is to predict or forecast number of passengers at t equal, for example, n+1, using recent n values, right? So here's the idea here is to use some recent values. For example, I need to use some recent values for predicting a next value, for example. This is the idea. So if, I mean, those companies, for example, you need to forecast, I mean, how much fleet we have, how much airplanes, how much services we need to provide. So sometimes this is very important to try to predict number of passengers expected using old values. So it could be 1-to-1, for example. I can just use a single value for predicting the next value, 1-to-1. It could be many to one. So in this case, we need to have a window, right? This window will have some number of values So this is also hyperparameter which you need to decide how many values, how many recent values you want to use to predict future values. So this is a data set, and here how it looks like. So for example, this is January 1949. We have 112,000. In February, it number increases to 118. In March, it's 132, and so on. So this is my time series. So if you want to use, I mean, we can, if you want to make it one-to-one, this is the original data set. If you want to make it one-to-one, so I want to use all the values. So I want to use 112 for predicting the next value, which is 118. So we need to reshape the data in this form. So I need to use, I have a time step, I mean just the most recent value, only one value for predicting the future value. So I need to use values at sample 0 to predict number of passengers at sample 1. So I need to use this one for predicting this one. I need to use this one again to predict this one, and so on. So this one will be xt, this one will be xt plus 1. So in this case, I need to, so the original number was 144. Now it will be 143 values, correct? Because we need to have this kind of time shift. I need to prepare my data. I need to create its time series. But in machine learning, we need to have some input features and we need to have some target feature. So now I need to prepare my, I can call this one, it's input features, right? This one will be target feature. This is the one which we want to predict. And in this case, how many features you will use, how many time series? It's only one feature, right? So just use xt. So it's 112, 118, 132, 129. So I need to use this one to predict this one. I need to use this one to predict 132. I need to use most recent value to predict future value in March, for example, and so on, or April, and so on. So in this case, you need to reshape your data in a format which fits RNN. So now I will use xt for predicting xt plus 1, for example, right? So, so the number of features, this is the number of features and number of time steps. Number of features is 1, and in this case, the number of time steps will be also 1, right? But also, if you want to increase, if you want to have a window of values, so for example, I want to use the most recent 2 values for predicting 2 future values. So in this case, if we will go to the original data, I want to use this value and this value for predicting this value. So I want to use the value at in March, in January, February for predicting the value at March. And after that, I will use the value at January, February for predicting it at April. So in this case, I will use the most recent 2 values. So in this case, we need to reshape the data into that format. So I want to use xt, maybe xt plus 1 for predicting xt plus 2. So in this case, we reshaped it into different structure. And in this case, we will have here 2 features, right? So now we have 2 features for predicting the third value. So, so just simply for multi-layer perceptron, we know it very well. The input must be in this format, number of samples times number of features. So the first dimension will be number of samples, and the second one will be number of features. So for example, if I want to use MLP here, so so at sample 0, how many features do we have? We have 2 features. So I will use this 2 for predicting this one. So if I want to use MLB for this problem, so how many inputs? I will have 2 inputs because number of features here is 2, right? So and I mean there is no connections between, I mean in MLB we don't have this kind of context. I will use the current input for predicting the future values. So there is no connection between sample 0 and sample 1. So at sample 0, I will use this one for predicting this one. When we go to sample 1, I will use this 2 values for predicting. So it's fixed input to predict this one. In the second sample, I will use those 2 values for predicting this one. So in feed-forward neural network, it will have only 2 inputs, right? So it's xt and xt plus 1. And the number of hidden layers may be here, I don't know. This is something which you need to decide. And the output will have only one output. I mean, the output layer will have only 1 neuron. So in this case, it will be like this one. So in case of MLP, we will have a model, and the model will have fixed input. Number of input will be number of features. In this structure here, we will have two values for predicting a future value, right? If you want to change, so if I want to use 3 features, as we mentioned before, so the model will expand. So we will add a third input here. So in this case, number of parameters will increase, the model will expand. And each time, if you want to change number of features, your model structure will be different. But in case of MLP, the data must be reshaped into this format. It will be number of samples times the number of features, which we know this anyway. But in case of LSTM, this one M, sorry. So in case of LSTM or RNN, we need to have the data in a 3D format. We need to create 3D data for RNN training. So the data must be in this format. It will be number of samples, the first dimension. The second dimension will be time steps, and the third one will be number of features. Time steps, this is something which you need to decide, right? This is a hyperparameter which you need to decide. So you can prepare your data, for example, for time steps equal 2, 3, 4, 5, and after that you can select the model which has better better performance. Yes. So in each sample, in fact, we will have some number of time steps. It's according to how many time steps and number of features. Yeah. So this one, it's prepare your data for training MLP. I mean, I got this code from a link. I put it here also. So it's just preparing the time series, preparing this one from this structure into this structure. This look back here, it could be maybe, it should be maybe number of features, right? So anyway, from this one, we will get the data from that format into that format. And we used here MLP for number of inputs will be 3, number of hidden units will be 8. So number of parameters here will be 8 times 3 plus 8, right? So it will be 8 times 3 plus 8. This is the number of parameters of the first hidden layer. And the output layer, we will have only 1 unit. But the number of inputs to this layer will be 8. So in this case, number of parameters here will be 1 times 8 plus 8. So the total number of parameters here will be 41. So total number of parameters here will be 41. Of course, we divided the data into one part for training, one part for testing. And when it's time series, we need to keep the order. This is very important. So you cannot shuffle the data, because if you will shuffle it, you will destroy time dependencies between values. So we need to divide it like this one. So we can just use 80% for training and maybe 20% for testing, but we need to keep the order. You don't shuffle your data in this case here. It's a prediction. So when it's a prediction, you can use mean square error. Maybe you can use mean absolute error, right? Because it's a prediction problem. So the loss function here, you need to select a loss function, which is suitable for the problem. It's not classification, but it's regression in this case here. Input dimension, in fact, it should be number. I mean, I need to modify this one. This one will be number of features. Number of features. Right? So input dimension, as we know, the input dimension will be number of features, right? So number of features here will be 3, for example. So in this case, we need to change this one into number of features, right? We calculate root mean square error for training and for testing, and we have those numbers, right? In case of RNN, for example, we need to reshape the training sequence into a 3D matrix. So the 3D matrix will have this dimension. It will be number of samples times number of time steps times number of features. So for our data set here, in fact, if you will use only one feature, so the data set should take this dimension. It will be 96 times 3 times 1, right? So it will look like this one. So so I have here one feature, in fact, right? So this is how the data. I'm using one dimensional data. I have only one feature, right? So and the time steps will be 3, right? So so I will use. I normalized, of course. I normalized the inputs. So this is the first value. This is a second value. This is a third value. I will use those three values for predicting number of passengers in maybe in this month. So maybe if it is January, February, March, right? This one will be March for predicting number. This one will be future value. In fact, this value is a value which is here, in fact, right? So this is the value, in fact, at April, right? Yeah. So this one will be this value here, correct? So this is the number of time steps, right? So time steps equal 3. Number of feature is 1. So when we train the model will run in a for loop, and each time we will consume one input. Each time we will train the model using this input, and after that we will go to the next time steps because I have 3 time steps. In the next time, of course, I will update here. Sorry, I will initialize the state h0 by maybe by 0 or some random value. I will use this input for updating the state. So here I will update the state. We will have h1, and after that I will use h1 here for, and I will use the current input for getting h2, and after that I will use h2 here with this input to calculate h3, and after that I will use this h3 for calculating the output here. So this is how it will work. So in fact, each sample we will train the model 3 times. You can just say. So this is sample 0, sample 1, sample 2. So each time we will train the model 3 times because I have 3 time steps. Number of features equal 1. So how can we reshape the data? It will be reshaped. I mean, this is the first dimension, which is the number of samples. This one will be a number of samples. This one, it's time steps. This one, it is a number of features. So we will train the model. We used the sequential API, and we added sample RNN layer, right? The input shape will be time steps times 1. In fact, it's time steps times 1. I mean 1, this is the number of features because I'm using only one feature in my time series, right? So it's not 2-dimensional, but it's 1-dimensional time series. So we have one feature each time. So each time step, we will consume only one feature, right? So we have 2 layers. One layer, it's sample RNN. We have here, you need to define number of hidden units in this layer. For example, this is the input shape. We have one dense layer, and this has an activation hyperbolic tangent, for example. So, and we will use mean squared error, mean absolute error. I mean, we need to decide which one will fit your problem. So this sample RNN, we will have 24 parameters, and the dense layer, we will have 5 parameters. Here, in fact, we used a number of hidden equal 4, right? So we have this number of hidden equal 4. So so those 5, it will be 1 times 4 plus 1. I mean those 5, it will be 1 times 4 plus 1. So if we need to calculate number of parameters here, I mean the input will be 3 times 1 because we have time steps, 3 times steps. We have one feature. This dimension, in fact, it's none because we don't care about this one because this is the number of samples. So the input will be 3 times 1. The output will be 4 because we selected number of hidden states, number of hidden units equal 4. So so number of parameters will be number of this hidden neurons. It will be 4 times x dimension number of features, which is 1. Plus hidden to hidden. I mean, this is this one. It's a hidden to input, right? So hidden to input, it will be 4 to 1, correct? 4 to 1. So 4 times 1 plus hidden to hidden, which is 4 times 4, plus number of bias here. Sorry, this one is not correct. This one, this is bias h, right? If we selected this one equal 4, so this pH will be 4. I need to fix this one. So this is RNN parameters. For fully connected layers, it would be 1 times 4 plus 1. So in total, it would be 29 parameters. We will have 29 parameters. Yes. So it's the same also. We divide the data into one part for training, one part for testing. So we keep the order because if we shuffle, we will destroy the time dependencies. So we will use this one for training, this one for prediction. So this is a training root mean square error for training set and for testing set. So maybe the performance is better in ML. No, in fact, it's 0.5, 0.1. Yes. Yeah. So it means that in the training, the RNN or sample RNN was much better than MLP, but in testing, MLP was much better than RNN. Yes, or sample RNN. Yes. Do you have any question for that part? Any questions for? Should we take a break before going to this LSTM?
Yeah, we could take like 5 minutes.
Okay. Okay. So we can just take 5 minutes and or 10 minutes. We can start again after 10 minutes.
Okay, thank you.
Thank you very much. Bye.